Hello students, this is Professor Chalai, and in this video we're going to look at some mole concept calculations. Now by the end of this video you should be able to easily convert between the mass of a substance to the number of moles of a substance to the number of particles of a substance. As always, you can follow along with our chapter 3 workbook. In the remainder of this class, one of the most sort of useful skill that you can learn is to be able to calculate the number of moles of a substance. Because as you will see throughout the rest of the semester, you'll go a long way to solving many problems in chemistry if you were able to figure out how many moles of substance you're dealing with. So being able to calculate number of moles, whether it's from the mass or the density or the concentration or the number of atoms, being able to figure out how many number of moles of things you're dealing with is going to be very helpful. Now, as I mentioned in the previous video, the mass that we use in a lab typically are on the scale of a few grams. So let's look at mass in grams. To convert mass from moles then, we need something that converts between grams and moles. And wouldn't you know it, the molar mass of a substance that we looked at in our previous video is in units of grams per moles. So to convert between the mass of a substance and a number of moles, we'll use the molar mass, or double M. To convert between number of moles and number of particles, we need to figure out how many particles are in 1 mole of substance, and that number is given by Avogadro's number, right, our symbol Na. Remember, Avogadro's number states that 1 mole is equal to 6.02, there we go, 6.00222 by 10 to the 23rd particles. And particles could be anything from atoms to molecules to grains of sand. Put another way, Avogadro's number can also be written as 6.022 by 10 to the 23rd particles per 1 mole. Okay, so let's look at some example calculations. Let's look at number 3 in your workbook. Here, the question is asking us to calculate the amount of carbon in moles given 0.0265 grams of pencil lead. And we're going to assume that pencil lead is just pure graphite, pure carbon. So, in this question, they're asking us to go from mass in grams, 0.0265 grams, to number of moles. We therefore need the molar mass. And since it's pure carbon, the molar mass will just be the same as the atomic mass of carbon. So the molar mass of carbon, which if you look up in your periodic table, you'll find is about 12.01 grams per mole. So we start with mass, and then we're gonna use the molar mass to get number of moles in this calculation. So we start with mass, 0.0265 grams. We're gonna use the molar mass, but we're gonna need to cancel out grams, so let's put the grams on the bottom, moles on top, grams cancel out, and if you plug those numbers in your calculator, you get something like 0.00206 and so on moles, but we need answers to 3 significant figures, so that becomes 0.00221 moles. Always remember to write your units. In this case, they're asking us for amount in moles, so here is our amount in moles. Let's try a different one. Let's try going from grams to number of atoms. So in this example, we need to go from grams all the way to number of particles, number of atoms in this example. Again, we can go from grams to number of moles using the molar mass, and then from moles to particles using Avogadro's number. You can pause the video and try to figure out number 4 for yourself, and then unpause and we'll go over it together. Okay, so we're starting with mass, 0.0265 grams, and we're gonna use the molar mass. Again, it's still the same pencil lead. We're gonna use the molar mass to convert that to number of moles, so that's 12.01 grams per mole. and that will give us number of moles. And then we use Avogadro's number to go from moles to number of particles. So using Avogadro's number, in Avogadro's number, it's 6.022 by 10 to the 23rd particles. In this case, the particles are atoms, so let's just put atoms for 1 mole. That way moles cancel out and grams cancel out, and we have as our units number of atoms, which is what the question is asking for. You plug these numbers in your calculator and you should get to 3 significant figures, 1.33 by 10 to the 21st number of atoms. A good way to check your answers, if you're dealing with number of moles or mass, those are more reasonable numbers that you're accustomed to. If you're dealing with number of atoms, those are going to be very large number, or number of molecules. They're going to be very large number of things. In this case, 10 to the 21st is the order of magnitude. So that's a way to check your answers. If you have a very tiny number of atoms, your answer is probably not correct. All right, you can pause the video. Try number 5 by yourself. When you unpause, I'm going to go over it step by step. Okay, so in number 5, we're asking for a number of copper atoms. So copper atoms, and that's the question they're asking us for. And they give us the mass of copper atoms. So the mass is 3.10 grams. This question also tells us what kind of atoms they are. They're copper atoms. And if we want to figure out the number of atoms from the mass, we need to know the molar mass of the molecules. In this case, they're atoms. So the molar mass of copper, if you look that up in your periodic table, you'll see that the molar mass of copper is 63.546 grams per mole. And so that will help us to convert mass to number of moles. But to convert to number of atoms, we'll also need Avogadro's number, which is a number that you should memorize, but it's 6.022 by 10 to the 23rd particles, in this case atoms, for 1 mole. So that's our units for Avogadro's number. So let's set this up. We start with mass. In this example, 3.10 grams. We use the molar mass to convert to number of moles, and we're going to put the grams on the bottom, so 63.546 grams for 1 mole, and that'll help us convert from grams to mole. And then we can use Avogadro's number to help convert from moles to number of particles. So Avogadro's number is 6.022 by 10 to the 23rd atoms per 1 mole. And so our answer comes out to be, if you punch all of these in your calculator, 2.94 by 10 to the 22nd atoms. Again, a large number of atoms, which makes sense for a copper penny. All right, I hope all of this is starting to make sense. We're just using molar mass and Avogadro's number as the in-between to go from mass to moles to number of atoms, or you can do the reverse. All right, number 6 is taking all of these concepts and presenting to you a little bit more of a challenging problem. So I would pause the video right here and try to struggle through with number 6 on your own for a while, and then you can unpause and see where we get to. All right, so number 6 doesn't seem like a very complicated question, but there are a number of elements to this question that you might not have recognized. So let's look at them. So we start with an aluminum sphere. So right away we know a couple of things. One, the material is aluminum, which is an element, metal composed of atoms. It's also a sphere, right? That's going to be important. They give us the number of atoms, so let's write that. Number of atoms is equal to 8.55 by 10 to the 22nd atoms. So right away you should be thinking, we have number of atoms, we can use Avogadro's number to convert to number of moles. Okay. Then they're asking us for the sphere's radius. So what is the radius of the sphere given the density So they give us a density. Let's use a different color. The density of aluminum is 2.70 grams per centimeter cube. All right, so we start with number of atoms. And we know that, well, if we use Avogadro's number, we can go to number of moles. Is that helpful? We don't know. But we know that if we use the molar mass of aluminum, which you look up at on the periodic table, and you'll find that it is 26.9815 grams per mole. So if you use the molar mass, then you know we can get to mass in grams. Well, that's starting to get us somewhere, because we know that we have the density. And so if we know the mass and we know the density, we can figure out the volume. So we can use the density to get to the volume. And at least that's getting us somewhere, right? Because we know this is a sphere, and we're looking for the radius of the sphere, and we know that the volume of the sphere is related to the radius, which we'll get to. So this is our strategy for the first part of the question, to just try to figure out what the volume of the sphere is. So let's start with number of atoms. 8.55 by 10 to the 22nd atoms. We're going to use Avogadro's number to convert to number of moles. And Avogadro's number is 6.022 by 10 to the 22nd atoms for 1 mole. And so I divide by it to convert to number of moles. And then we can use the molar mass to convert to mass. And the molar mass for aluminum, again, is 26.9815 grams per mole. We put mole on the bottom so that it can cancel out. And then we can use the density to convert from mass to volume. And the density for this sphere is 2.70 grams per centimeter cube. And we put grams on the bottom such that the mass could cancel out, and we're left with the volume in centimeter cube. And this makes sense because volume can be measured in centimeters cube. All right, so if we punch all of these numbers into our calculator, we end up with a volume of 14.2 centimeters cubed. Right, to 3 significant figures, we get 14.2 centimeters cubed. Okay, that's one part of the problem. Now we're told that this is a sphere, and the volume of a sphere, if we remember, is equal to 4/3 pi r cubed. We know the volume, we just need to find r. Now before I plug numbers into here, I usually like to rewrite the equation such that we're actually solving for what we want to solve. And what we want to solve for is r. So let's see, how do we solve for r? Well, if we divide by 4/3 on both sides, right, we get 3/4, right? Dividing is the same as multiplying by the inverse. We divide by pi on both sides, so we get pi over there. And then we cube root the whole thing, right, to get rid of this cube. So that gives us r is equal to the cube root of 3 times the volume divided by 4 times pi. So all then we need to do is plug in the numbers for those. 3 times the volume that we solved for was 14.2 centimeters cubed. 14.2 centimeters cubed divided by 4 times pi. Pi is just 3.1415 and so on. You can just use, if your calculator has the a pi symbol, just use that. But if you plug all of these into a calculator, the cube root of centimeters cubed, the units should just be centimeters, right? Cube root of cm cubed is just cm. These numbers plugged into our calculator to 3 sig figs, right? 3 sig figs there, gives us 1.50 centimeters for the radius. So what started out as a very complex problem, through the slow methodical process of trying to start with what they give us, number of atoms, we know that we can use Avogadro's number to get moles, molar mass to get mass, density to get from volume from mass, and then using the formula for the volume of a sphere, we can then figure out the radius. Okay, that's it for number 6. I'm gonna let you pause the video now and answer numbers 7 through 11. I'm gonna answer them as well, but I'm gonna speed up the video so that you can slow it down and follow along if you wish. Otherwise, you can just use it to check your answers for numbers 7 through 11. All right, here we go. Okay, so I thought I'd do a little bit of a voiceover as I'm solving these, just so that you understand some of the different steps that I'm taking. For all of the parts of this question, I'm just solving them by counting up the number of atoms, looking up their atomic masses on the periodic table, and just adding all of those up. So in this example, there's 8 carbons, 10 hydrogens, 4 nitrogens, 2 oxygens, and I'm just adding up all of their atomic masses together. Now, note that formula mass has units of atomic mass units, whereas molar mass, which I'm solving for in these problems, has units of grams per mole. Okay, for number 8, we need to find a number of molecules given a mass. So we know that to go from mass to number of molecules, we first need the molar mass of the compound, which we can find by just solving for the molar mass of ibuprofen. We have the formula, so that's easy. They give us a mass, but it's not in grams. We can convert to moles using the molar mass, but we also need to make sure that we convert the mass to grams before we do that. And then once we have the number of moles, we just use Avogadro's number to figure out number of molecules to take us from moles to molecules. In these examples, always make sure that your number of significant figures match. The same for number 9. We have a mass of aspirin, but to convert it to number of molecules, we need to figure out what the molar mass of aspirin is. We just look up the atomic masses and we add them all up. We get 180 grams per mole. Again, in this example, we have milligrams, so we need to make sure we convert milligrams to grams before we can convert grams to number of moles. And then we can use Avogadro's number again to solve for number of molecules. Just always make sure that your significant figures match. Okay. In this question, we're looking at water. We should know that water has a formula of H2O, so to find the molecular mass of water is just 18.02 grams per mole. You should probably memorize that because you're going to probably use that a lot. So we're starting with molecules, which means we need to use Avogadro's number to convert number of molecules to number of moles, and then use the molar mass to convert number of moles to grams. So this is going backwards in that conversion that I showed earlier. And then for number 11, this is a little bit more difficult question. We have lignin that's burning to give carbon dioxide gas. So we have 31 atoms of carbon in lignin, which means we'll form 31 moles of carbon dioxide. As always, we need to find the molar mass of lignin by just adding up all of the atomic masses. And this will help us to convert the mass of the tree bark, 1 kilograms, to number of moles. But again, kilogram needs to be converted to grams first before we can convert the number of moles. So we have 1.72 moles of lignin, but we need molecules of carbon dioxide. But we know that according to this equation, for every 1 molecule of lignin, we get 31 molecules of carbon dioxide. So we can use that ratio to figure out the moles of carbon dioxide, which is 53.3. Now all we got to do is use Avogadro's number to convert that number of moles of carbon dioxide to molecules of carbon dioxide, always remembering the number of significant figures. That will bring us to the end of this video. I will see you in the next video when we look at empirical and molecular formulas. See you then. Bye.